if you have the closed, use the closed circle if you have the equal sign involved. Use the open circle if you do not. Okay, here's an example. We have x is less than 6. So here's my number line. It's a positive 6, so I locate my positive 6. I want to go ahead and draw an open circle because I do not see the equal sign. And I now want to determine which way do I make it go. Well, because I'm saying x is bigger than 6, I need to encompass all of these larger numbers. But if, notice this is written kind of backwards as far as we're concerned, the x is over here. But if you read it from the x, you'll see that this is exactly the same. And this says x is greater than 6. So this is exactly the same as that. But if I were to read 6 is less than x, you might not be as sure which direction you should draw your arrow. So wherever you see the variable, read from the variable, and then see if that helps you determine which way to draw your arrow. So this one, just because I'm looking at it immediately, I see the equal sign, so I want to use a colored in dot. Because it's the positive number 3, I want to put this colored in circle over the number 3 as opposed to a negative 3. And now I want to say to myself, x needs to be bigger than 3. So I know that's all these numbers over here to the right. Down here, I would read this. X is less than or equal to negative 3. So I want to, because of the equal to, I want to go to my negative 3, draw the closed in circle up above it, and now I want the x to be smaller than negative 3. Well, everything smaller is going to the left. So that's what's happened there. Okay. All right, unit rate. Sometimes they'll ask you, who's driving faster, or what is the better deal? Here's an example. Somebody's gone 350 miles in 5 hours. And then another person has gone 426 miles in 6 hours, and they want to know which one drove faster. Well, your best thing to do is to get them both to the same time frame, which would be 1 hour. We want to get it to that unit rate. And if you set it up to where hours are next to hours, then you're going to get miles next to miles. So this tells you always multiply the two things diagonal and divide by what's left. Well, 350 times 1 is still 350. Divided by 5 is 70. So this person is going 70 miles in 1 hour. So now we want to do the same thing here. 426 times 1 divided by 6. So at this point, I've already done this, but I'll just show you if you have your calculator. 426 divided by 6 equals 71. So this person has gone 71 miles per hour. And then the question is, who's driving faster? Well, this person who went 426 miles went faster by just 1 mile an hour. All right, here's an example of maybe some food and you're trying to see which is the better buy. So again, you want to set it up so we both are getting to 1 single ounce. So this tells me multiply this, divide by this. So I've got 3.15 divided by 16 equals, okay, and I'm going to put this 0.196. I'll just put 196 because we don't have 3 digits, and I'll show you what I'll do with that in just a minute. Then I'm going to put the next one in, same thing, multiply the diagonal and divide by what's left. 4.05 divided by 18 ounces, I get 0.225. Now we want to know which one is the better deal. I'm going to make this just 2 digits, and so I would round this one, and because it's money, this one's going to become 20 cents. Because that 6 is going to make the 9 go up to 10, which causes that to roll over and become 20 cents. So this is approximately 20 cents an ounce. But this one, this 5, is going to cause this 2 to become a 3. So this one is pretty much 23 cents an ounce. So the first one is the better deal. That would be the better food item to buy. Okay? Always, when you're presented with 3 parts of something and you're looking for the 4th, make sure you've got your ounces next to ounces or your miles next to miles and hours next to hours. But then you will multiply the 2 things diagonal and divide by what's left, and it'll give you that missing piece. Now, linear equation versus nonlinear. And I know this is really brand new to most every one of you. A linear equation is written like this. And this says y equals mx plus b. And a few minutes ago, I pointed out that the m stood for slope, which is another way of saying the rate of change. But we don't need to get too hung up on that. And linear is just like it sounds. It's involving a line. Nonlinear has no line. Okay, so, and in the nonlinear formula, you will or you could have exponents involved on the x or the y. You will never have exponents on this if it's a linear equation. So if they ask you, is this a linear equation, and you see something like this, but it has x to the 3rd power, you'd have to say no, because linear equations will not have exponents. Okay, the x and the y are the 2 coordinates, like from your coordinate points. You know, when we have the something like this, 3, 2. This is the x, this is the y coordinate. The m is the slope, and the b right here is the y-intercept. That just means where the line crosses the y-axis. For instance, here is, let me do it in black. Here is your grid. Your line is going something like this. This point right here is the B. It's where it's crossing the vertical line, which is the y-axis. Okay, that's the y. This is the x. All right, so if we look at a equation and it says 3/5 x plus y equals 7, this does not look like that. We want the y by itself on the left, and we want everything else on the other side. So we need to rearrange this to make it look like the above, mx plus b. So I want to move the 3/5 x over to the other side. So I do that by subtraction, do it to both sides. That cancels out, leaving me just the positive y, so that much looks alike. Then I've got, because it was negative, it stays negative because you cannot combine these 2 things. They are not like terms. And then we add it to a 7 because this was a positive 7. So now it actually looks like this formula. So we still don't know what the y coordinate is. We don't know what the x coordinate is, but we do know that the slope is negative 3/5. That's another explanation for another day. And the 7 is where it would actually be crossing the y-axis. Okay. All right, some tables and charts. The x and the y are just like the x and the y coordinates that I was just speaking of. So you might have a chart that would look like this. The chart can also be what they call a T-chart. And the same thing, we could have a 3 right here, and a 5 right here, a 0 right here, and a 1 right here. It would be just like that. Same thing here. 3 and a 5 and a 0 and a 1, or a 3 and a 5 and a 0 and a 1. And these would tell you to go over to 3, 1, 2, 3, and up 5. 1, 2, 3, 4, 5, and find where that point is. So that is 3, 5. Okay? All right. Functions, which is what this is right here, is f of x. But it could also be f of anything. I could have f of a, f of g, f of z. F of x is read the function of x. And I want you to think of a function like a machine. And if you put one number in, the x value, in this case, if I put a 3 in the machine, and the machine does a specific act, and it puts out, or it gives you the output of the y, or the f of x, the function of x, I would get a 5 in this case. That's just because it's told me that. The y value is also known as f of x. So this is the y value. So all you need to know about a function is it's like you've created a machine. And when you put one number in, you're going to do some specific act, whether it's adding 2 or subtracting 1 or dividing by 20. And then it's going to spit out a new number. The big important thing is that each time you put an x value in, it only has one unique y, or fx, that will be spit out. So every time I put a 3 in, because I've told you it's a 5 right here, I'm only ever going to get a 5. So if I later put a 3 in and I got a -2, that lets you know that that is not a function. So here's an example. On this case, I put in a -1 in the x. That's like putting it into the machine. The machine does what it's going to do, and it spits out a 0 for the y coordinate, or the f of x. Well, then a little while later, I put another -1 in. I should get exactly the same coordinate if it's a function, if the machine is working properly. But it's not. Spit out a different number. So this is not a function because I got two completely different answers for the same x. Now, if I had a 0 and a 0 down here and two different numbers up here, that's okay. That's not a problem. But if you get an x, it can only have one right answer. It could never have two y values. Okay? Also, if you can draw a vertical line and it only intersects the graph once, it is a function. So this blue line is this vertical line test. So here we have something, and the question might be, is this kind of curved backwards C, is it a function? Well, when I draw the line down, I realize no, it's not, because this line crosses in two places. And what's happening is, this looks like it is the graph right here of, let's just say that this is, okay, this point right here looks like it would be over 1, but down -2. But when I'm up here, it looks like the answer is over 1, but up 1, 2, 3. So notice the x's are the same, but they're spitting out two completely different numbers for the y coordinate. So this is not a function. But over here, when I draw the vertical line, even though I'm drawing numerous vertical lines, it's only crossing the graph at one particular point. And so this is a function, even though it's kind of, up and down, that's a function. However, if it had been drawn like this, vertically, it would not be, because look at all of the times it would intersect. So this is not a function. Okay. And then the last page. All right, stem and leaf graph. I really was not familiar with this. I don't know if you'll ever see it again, but it is on this little test. So pay attention to the key. The key is going to tell you what some of this means. The stem is the beginning portion, and this second half of the key tells you what these numbers mean. So this is telling you that the 0 means this. So they're actually just taking the stem of what looks like 112, but it's really not 112. This is the thousandths, the hundredths, and the tens column. So this is 1,120. That's what that would be. So the next one would be 1,123. The next one, 1,125. So maybe that'll help you a little bit. So just pay attention to the key. And sometimes the key may tell you whether this line is representative of a decimal point. So be aware of that. Percents, I just want you to remember one of these two formulas so you could do your percents. If you use this first one, be sure that you change the percent either to a decimal or even a fraction. And then you're going to either divide or you're going to multiply. Here's an example. There are 30 students in class. 3/5 of the students passed the test. How many students passed? Okay, we got to figure out what we're looking for and what we have. We are looking for the part because it says how many students passed. I don't know how many students passed, but they did tell me how many students were in the whole class to begin with. And that was 30. So they're actually, even though it's not in the form of a percent, every fraction is a percent. So I am to end this, the fact that I've got this word of, that denotes multiplication. So I want 3/5 of the 30 students. So 3/5 times 30. So now don't forget what you know about fractions. So I put in the 3/5 times the 30 over 1. I could multiply straight across and then I could divide, but I like to divide first, especially if it's easy. And 5 will go into 30 6 times, and 3 times 6 is 18, so that is telling me that 18 students passed. In this case, they are giving me, I can use this formula over here, and I could put, I don't know the part. Let me get a blue one so it'll make more sense. I don't know the part, so I've got, that will leave blank. So my percent is going to be this 3/5. And I got my 100 down here, and I've got my 30. Well, this formula always tells you, multiply those two things and divide by this. So you will multiply this 30 times the 3/5. What did I, wait a minute.